Okay, in this next example, we're going to look at the IMDb document classification problem. So here, the observations are actually documents, short documents, which each one is a review of a movie, right? So we've got sentences in it and words and so on. And there's a sequence to these, right? The sequential data. But the first model we're going to fit is going to use a bag of words representation. And so in this case, we restrict the dictionary to 10,000 words in the English dictionary, and these are somehow the top important 10,000 words. And we're going to score our document for how many times each word appeared in the document. So that means we'll have an observation vector of length 10,000, mostly 0. And to make this easy for this lab, we actually pre-prepared the data, and that's where we're going to start.
Okay.
And Jonathan will tell us what we do next.
Thank you, Trevor. And we'll also compare that to at least one sequential model. There are various sequential models one could apply to this, but we're just going to try and contrast the bag of words to the sequential one here. Okay, so the general structure will follow a similar pattern to we've seen to the examples we've seen so far. So we're going to skip to where we specify our model, and it's going to be a pretty simple model with one hidden layer here. And our network specification is very similar to the headers data. Recall we have to call this super function so that Torch knows it needs to do this in order to be ready to fit. Okay, so the rest of the specifying the model and fitting is very similar to the headers and the MNIST as well as the CFAR data.
So Jonathan, in this case, would input size be 10,000? And it's going to 16 hidden units?
Yes, that's right. Yeah. Yes, and thank you. Yes, so this is where we tell what the input size is, and it says, well, this is the X trained tensor, and this is the number of columns of it.
Yeah.
10,000. Okay, and you can see the summary here. There are 3 stop words that are included.
3 stop words.
Yes, but morally 10,000 features here. Okay, so let's just specify our model. Again, instead of regression, it's binary classification. And we can make a similar plot to the other examples and track.
There were 25,000 training examples and 25,000 tests.
Yes, and we achieves an accuracy about 85%. And since this is a relatively simple model, the bag of words model, we can use other methods, like other linear methods, or regularized methods like the lasso.
So the response was sentiment, which is positive or negative, right?
Yes, whether someone likes the movie or not. That's right. Okay, so we're going to compare this to logistic regression with the lasso. And I guess of note here, we see we're going to use sparse data representations for the training and test because we have, 25,000 cases in each training and test and 10,000 features. If those were full matrices, those would be pretty big.
But of course, most of the data matrix is going to be zeros because the documents are all short, and so most of the words in our dictionary aren't going to be used.
Yeah, so if we didn't use sparse matrices here, this would be really very memory intensive to load and very expensive to fit. Okay, so
this is sort of ideal problem for lasso as well, when you've got very wide data sets, in this case 10,000, and you don't expect all the features to be important for this task.
Yes. So let's see how well the lasso does. We're going to, what we'll do, we'll compute the solution path and evaluate test data along the solution path and compare that to the test score for the neural network as a function of epoch. So I'm just going to skip to the plot here. So we compare training and test error, black and blue, between the two methods. And so the x-axes here are different. On the left-hand side, this is the lambda parameter for the lasso, and we see going from a very sparse solution to a denser solution. It has an accuracy in the low 80s, which is quite similar to the right-hand side here. This is our single hidden layer neural network. And what this example shows is that sometimes the neural network, is not necessarily necessary to get a good performance. And in this case, we have about the same. And I should say at the dense end, it's about 83%. I think it peaks here at about 88%. So it does slightly better on test data. Yeah. But that's not that big of an improvement, but still slightly better. Okay. So we're going to compare these bag of word models to a simple, a sequential model for document, for the IMDb data. So we're going to use this LSTM, so long short-term memory recurrent neural network, and you can read about the structure of that in the textbook. We'll see, in order to specify it, is actually pretty simple. We're going to combine that with this embedding representation of the words. And we'll ultimately want to compare the accuracy. So again, we have to construct our data loader. For all of these different views of the IMDb data, actually there's a different form of the way that the data is represented. It's for the sequential models, it's important to have a sequential representation. So each, rather than just reducing the document to the number of times each word appears, we actually have to track the order of the words.
So in order to set the data up here, the documents were restricted to length 500 words. So if a document had less than 500 words, padding was used, just with blanks. Mm-hmm. And if it had more, it was truncated, so use the first 500 words.
Okay, and so a document now is represented as a 500 by 10,000 one hot matrix that sort of indicates, which word appeared at which time in the sequence of length 500. So this embedding layer is going to take these 10,000 words and reduce that to 32. So then we'll have something like a 500 by 32 representation of a document as we move along the sequence. And then we use this LSTM model that sort of tries to fit a sequential model or some kind of time series model to the data, using 32 units, which we've used the embedding layer to reduce it to. So that's a rather complicated thing to describe, but actually it's surprisingly easy to sort of specify this in code. Okay, so this is how we're going to specify both the embedding and the long-term LSTM model in the network. So input sizes is again about 10,000. So we're going to ask for an embedding layer of 10,000 input and 32 output. So this actually is going to incur roughly 10,000 by times 32 parameters. So that's going to be about 320,000 parameters just for this. And then we're going to have this, once we reduce to 32 dimension, we're going to use this sequential model, the LSTM model, to take account of the temporal aspect. And then finally, we take those 32 units and we map to 1 again because we have a binary classification task. And the rest of the fitting is, once we specify the form of the network, is again similar to all the other examples. Let's just jump ahead and take a look at how this model performs. In the end, it gets about test accuracy of 85%. So pretty comparable to the bag of words and to the lasso in this case. So I see a few things with this example. One, that the Torch and other packages have, it's easy to specify complex models, this embedding and recurrent neural network model, but they don't always perform better than linear models or other simpler models.